Good day everyone. Myself Vaidegi working as assistant professor in Sri Muthukumaran Institute of Technology, Mangadu. Today the video lecture is from the subject EC 3452 Electromagnetic Fields for 4th semester ECE students. The lecture is from the second unit electrostatics. The topics are electric flux density, boundary conditions and capacitance. In this lecture, we are going to explore some of the most fundamental concepts in electrostatics that forms the basis for understanding electromagnetic field behavior in practical engineering applications. The key topics covered include electric flux density, dielectric constant, boundary conditions at the interface at different materials, and the concept of capacitance in various geometrical configurations. These principles helps us understand how electric fields interact with the materials, how charge is distributed across boundaries, and how electrical energy is stored in capacitive systems. A clear understanding of these concepts is essential for designing electronic devices, transmission systems, and energy storage components used in modern electrical and communication engineering. First, we see about the electric flux density and the dielectric constant. The electric flux density, denoted by the vector D, represents the amount of electric flux passing through a unit area of a material placed in an electric field. It is directly related to the electric field intensity E by the relation D is equal to epsilon E, where epsilon is the permittivity of the medium. The permittivity is given by the product of vacuum permittivity epsilon naught and relative permittivity epsilon r, which is also known as the dielectric constant of the material. The dielectric constant indicates how easily a material can be polarized when subjected to an external electric field. As polarization increases, the effective electric field inside the material decreases, allowing the material to store more electric energy compared to the free space. Next we see about the behavior of flux density in different media. When an electric field passes through different media such as vacuum and dielectric materials, the distribution of electric flux density changes significantly. In vacuum, both the electric field E and electric flux density D are directly proportional and remain collinear because there is no polarization effect. However, when the field enters a dielectric material, the molecules within the material become polarized. This polarization reduces the effective electrical field strength inside the material while only slightly affecting the electric flux density. As a result, the electric field lines appear compressed within the dielectric medium. This behavior plays a crucial role in understanding how insulating materials enhance the performance of capacitors and reduce unwanted electric field effects. Next we see about the boundary conditions of the electric flux density. At the boundary between two different dielectric media, the electric field does not remain uniform and must satisfy certain conditions known as boundary conditions. One important condition involves the normal component of electric flux density. According to this condition, components of D in the two media is equal to the interface. Mathematically, this is expressed as D1n minus D2n is equal to rho s, where rho s represents the surface charge density. This condition helps determine how electric flux behaves when it passes from one material to another, especially in systems involving layered dielectrics or insulation materials. Next, the tangential component and the perfect conductor case. Another important boundary condition applies to the tangential component of the electric field intensity E. At the interface between two dielectric materials, the tangential components of the electric field remain continuous, ensuring smooth transition of field lines across the boundary. However, in the case of a perfect electrical conductor, the tangential component of the electric field becomes zero. This means that the electric field must always be perpendicular to the surface of a conductor. Additionally, all excess charges in a conductor reside on its surface, and the normal conductor of component of electric flux density at the surface is equal to the surface charge density. These properties are very useful in shielding and grounding applications. Next we see about the electrostatic boundary value problems. The electrostatic boundary value problems involve determining the electric field potential or V or electric field E within a given region by solving fundamental differential equations. When charge is present within the region, the potential is governed by Poisson's equation given by del square V is equal to minus rho by epsilon. In charge-free regions, Laplace equation is used, which is expressed as del square V is equal to 0. Solving these equations allows engineers to analyze electric field distributions in complex systems such as capacitors, transmission lines, and microelectronic circuits. These mathematical tools are essential in designing efficient electrostatic devices and understanding how fields behave in different configurations. In between that, we have to see the types of the boundary conditions. There are three major types of boundary conditions used while solving electrostatic problems. The first is the Dirichlet boundary condition, where the electric potential is specified on the boundary surface. The second is the Newman boundary condition, where the normal derivative of the potential or electric field strength is specified. The third type is the mixed boundary condition, which combines both the Dirichlet and the Newman conditions of different parts of the boundary. The choice of boundary condition depends on the physical constraints of the system and helps in accurately predicting the behavior of electric fields within electrostatic devices. Next we see about the capacitance and its basic concept. Capacitance is defined as the ability of a system to store electric charge per unit potential difference between conductors. It is mathematically expressed as C is equal to Q by V, where Q is the charge stored and V is the applied voltage. The unit of capacitance is farad, which represents 1 coulomb of charge stored per volt of potential difference. Capacitance depends mainly on the geometry of the conductors and the distance between them and the dielectric material placed between them. Understanding capacitance is extremely important in applications such as filters, oscillators, energy storage devices, and communication circuits. In that energy storage, we have to see that when a capacitor is charged, electrical energy is stored in the electric field developed between its conducting plates. The energy stored in a capacitor is given by the expression W is equal to 1 by 2 CV square. This stored energy can be released whenever required, making capacitor useful in power supply systems and electronic circuits. The amount of capacitance increases when the area of the plates increases or when the separation between the plates decreases. Additionally, inserting a dielectric material between the plates increases the capacitance further by reducing the effective electric field strength and enhancing charge storage capacity. Next we see about the parallel plate capacitor. A parallel plate capacitor consists of two conducting plates separated by a dielectric material. The capacitance of this configuration is given by the formula C is equal to epsilon A by D, where A represents the area of the plates, D is the separation distance between them, and the epsilon is the permittivity of the dielectric medium. This type of capacitor provides a uniform electric field distribution between the plates, making it one of the most commonly used capacitor structures in between them. By inserting a dielectric material between the plates, the capacitance increases by a factor equal to the relative permittivity of the dielectric. Next we see about the cylindrical capacitor. A cylindrical capacitor consists of two coaxial conducting cylinders separated by a dielectric medium. The inner cylinder has a radius A, while the outer cylinder has a radius B, and both share a common length L. The capacitance of this configuration depends on the logarithmic ratio of the radii and is given by C is equal to 2 pi epsilon L divided by ln of B by A. The electric field in this type of capacitor is radial in nature and varies with the distance from the center axis. Cylindrical capacitors are widely used in coaxial cables, high frequency transmission systems, and various sensing devices due to their symmetrical electric field distribution. Next we see about the spherical capacitor. A spherical capacitor consists of two concentric conducting spheres separated by a dielectric material. The inner sphere has a radius A and the outer sphere has a radius B. The capacitance of this configuration is given by C is equal to 4 pi epsilon AB divided by B minus A. In this special case, where the outer sphere radius approaches infinity, the capacitance reduces to C is equal to 4 pi epsilon A, representing an isolated spherical conductor. Spherical conductors are commonly used in high voltage applications, electrostatic shielding, and precision measurement instruments such as electrometers and charge detectors. Finally, we came to the summary of the lecture. In summary, the electric flux density established the relationship between electric field intensity and the permittivity of the medium. Boundary conditions helps us understand how electric fields behave at the interface between different materials. Capacitance allows electrical systems to store energy in the form of electric fields, and its value depends on the geometry and dielectric properties of the system. Different capacitor configurations such as parallel plate, cylindrical, and spherical capacitors provide specific advantages in practical applications. Together, these concepts form the theoretical foundation for analyzing and designing a wide range of electrical and electronic concepts. Hope you all understood. Thank you.